Okay, so I start. Thanks for coming. So it's my great pleasure to be invited to speak in this derived seminar. Although probably my talk will not be so derived. So as you see, today I will explain the geometry of Gopakumar-Vafa theory. So basically, it's a curve counting, and this is like a curve counting theory. So the purpose actually is listed in the first page. So focus will be enumerative geometry for Calabi-Yau threefolds. So this is a subject which has been studied intensively for decades, so a few decades, with motivation from mathematical physics and classical enumerative geometry. So in particular, there are rich structures for the curve counting invariants, like the Gromov-Witten and Donaldson-Thomas invariants. And the purpose of today's talk, actually, I would explain this arrow, where the structures of enumerative geometry for Calabi-Yau threefolds actually influence the more classical geometry for the certain modular spaces. And this involves the Higgs modular space, for example, the modular of Higgs bundle and the topology of hitching vibrations, and also the topology of the holomorphic symplectic manifolds. And also it would be relevant to some modular of semi-stable sheaves on some final surfaces like P2. P1 cross P1, and so on. Okay, so this is so basically I would see that actually the classical geometry of these varieties, which were, these are certainly was studied much longer time, actually are constrained in some sense by the enumerative geometry of Calabi-Yau threefolds. So I will explain this connection. Okay, so let me start my talk. So I will start with the left part of the previous page, namely the enumerative geometry. We are interested in counting curves in Calabi-Yau threefolds. So to start with, I consider X beta a pair where X is a smooth Calabi-Yau threefold, beta is curve class. So as I said, we're interested in counting holomorphic curves in X lying in the class beta. So, and in physics, there are certain numbers which are predicted to do the job, which are called the BPS invariants. So these numbers are they behave nicely. They are we use the notation n g beta to denote the virtual counts of genus G. So there are two parameters, right? When you fix X, you will fix beta, then you need a genus. This counts the genus G curves in the class beta. So first, since it's a counting problem, so expect these numbers are integers. They're integers. And when you fix the curve class, the homology class, then expect when the genus grow when the genus is very large, then there won't be curves of genus G of that genus in this curve class. So you expect some vanishing. And moreover, this number, which means for every fixed genus, for every fixed pair X and beta, there are only finite many invariants. Actually, these invariants are also expected to govern all the other curve counting invariants, namely like Gromov-Witten and Donaldson-Thomas. So this is a prediction from physics. The existence of this invariance. Any question at this point?
Can I ask why beta is now an integer? It used to be a class, and now why it's an integer?
No, this is just a prediction from physics. So of course, if you do Gromov-Witten counting, then there will be rational numbers, but so the prediction is that there are, for every genus, also for every beta, there are finite many integers which govern all the other.
Yeah, where beta lives. So it used to live in second homology, and now
beta is here. Beta is here.
But downstairs, there's a
parenthesis missing.
I see.
Mm-hmm.
Yeah, just in the next line you say like as if beta was sitting inside Z.
Okay. All right. So is it okay so far? Great. So now so the first question is how to define these numbers. Okay, so the more traditional way is more traditional or indirect way is to first we get some curve counting invariants and do the transformation and give you back this ng beta. So the traditional way is to use intersection theory on certain modular spaces. So there are two the typical ones. So which depends on how you describe the modular problem. So one of them is the Gromov-Witten theory, where again this is parameterized. So the parameters here are the genus and the beta, right? So the Gromov-Witten theory considers the modular space of stable maps from a genus G nodal curve to the Calabi-Yau threefold, and so we consider a curve as a stable map, and then you fix the image, which is beta, And the stability condition is that you want the automorphism to be finite. Okay, so then this model, and then there's a long story, and so the invariants are given. So this modular space in general are highly singular, but there is a so-called perfect obstruction theory, which tells you that you can do intersection theory there, which behaves like an intersection theory on a smooth manifold. So you do the intersection theory, you get a virtual fundamental class, and you get numbers, which are rational numbers. And here they're rational simply because the automorphism could be finite. So you can't curves with a weight given by some rational numbers. You have to divide by the automorphism. Okay, so this is the first way where for x and for g and beta, you can get some numbers, and the other way is to so-called Donaldson-Thomas theory, and there are a lot of variants of it. So here I'm using the classical one in some sense. So the one here is that we can view a curve as an ideal sheaf. So for that, we fixed Euler characteristic of the structure sheaf of the curve. So then there is a parallel theory here where you can define the dt invariants. Now the parameters are the Euler characteristic and the curve class. Okay, so these are two, in some sense, traditional way for defining curve counting invariants, and they are studied for decades. So the Gromov-Witten and the dt invariants, which concern complete different geometry because they use complete different modular spaces. So, and it's amazing predictions that they actually give you the same information. So this is the MNOP conjecture, Maulik, Nekrasov, Okonkov, Panda, and they are, of course, now solved for many cases like complete sections, toric varieties. So, okay, so although these numbers are known, these numbers are defined, but people are looking for actually a direct definition of the BPS numbers and G beta. Actually, so of course, if the more traditional way is that you first define the Gromov-Witten or dt invariants and then use these numbers to define this NG beta. And to show that these numbers are well defined, namely they are integers and satisfying the vanishing properties, this requires to prove a bunch of properties for the original Gromov-Witten invariants. But the only thing I want to emphasize here is that this transformation is really very complicated. So here I'm listing the equation, so the left-hand side are, if you know the Gromov-Witten invariants, then assume you want to get this BPS numbers, you have to use this equation. So the left-hand side, everything's known in the left-hand side, but the right-hand side is pretty complicated, and these complicated factors are coming from the multiple covers. Because the Gromov-Witten, it's like we can't not only embed curves but also count multiple covers, and this will cause the complication which given by this factor. So but there is a something which is not very satisfactory is that so you see that even so for this equation, then both the left-hand side and the right-hand side are parameterized by or indexed by the genus and beta. However, as I said, the issue is that to discuss the left-hand side, also to define the left-hand side, you have to involve multiple cover because you are doing stable maps, which means it's not like one-to-one correspondence, right? Obviously, and even worse, in order to define a single invariant in G beta, you need infinite many numbers here to define even a single one here by using this equation. Meaning that to define a single, if you just want to know the counting of genus G and the class beta, you can get this number with infinite many. So you cannot immediately get this number within a finite type modular space because you really have to use infinite many mg x beta for many G, and then you get a single invariant. Or if you do the Donaldson-Thomas theory, there's a similar story. However, this idea of the Gopakumar-Vafa from physics, so they proposed a way to get these invariants directly via a finite type modular space. And this is the idea. So you just start with a finite type modular space, and then you can get all these invariants. And these invariants will give you the same information as the Gromov-Witten invariants. Okay, so this is the main topic I'm going to discuss today. So here is the It's just let's start with the Gopakumar-Vafa theory, which is the proposal I was just talking about. So in physics, this was introduced in Gopakumar-Vafa paper in, more than 20 years ago. Then a lot of mathematical theory are following up. So first, this is the work of Hosono-Saito-Takahashi, and then Kiem-Li after 10 years. Then Maulik and Toda. So each work is built on the previous case, a previous work, and which covers more cases, and which somehow get a better understanding of the original physics proposal of Gopakumar and Vafa. So okay, so here I'm following the idea of Maulik-Toda and Toda, these two. So the idea, let's start. The idea is listed in this page, namely, okay, we consider the pair X and beta, the Calabi-Yau threefold, and a curve class. Just let me clarify that it's before. So it's a Calabi-Yau threefold and curve class. Okay, now we want to define the curve counting invariants. So how to do that? So we first make some extra choice, namely, okay, it's first a natural choice that we want to make this Calabi-Yau threefold polarized. We give a polarization of the Calabi-Yau threefold. And then there is a crucial choice, which is a number. So we make an extra choice, which is the chi, an integer. So just we choose an integer. Then we can have a modular space of semi-stable, Giesecke semi-stable one-dimensional sheaves on X, with whose support is in this class, and all are characteristics given by this chi. So namely, after you get X and beta, we make an extra choice of chi, so we can consider a modular space of one-dimensional sheaves, one-dimensional coherent sheaves supported on the curve in the class beta. All right, so these are something like that. And this modular space, so here the stability conditions with respect to this the slope. Okay, so and here this modular space admits a natural structure, which is the Hilbert-Chow morphism. Namely, you can send a coherent sheaf to its fitting support. Basically, you forget about the sheaf, but just remember the support. And this actually gives a morphism from this modular space to the Chow variety. Okay, so let me briefly say what the idea is here. So because you want to get a modular space which parameterizes curves in the class beta. So one of the good candidate is the Chow variety, right? So you give an X and beta, you consider, so there is a variety which parameterize, a scheme which parameterizes one cycles in the class beta. However, you cannot count curves there because you don't see the information of the genus. So the Chow variety gets you all the one cycles in class, the curves in the class beta, but you don't see the genus, the information of the genus of these curves. So to solve this problem, we'll have to consider this relative geometry. Namely, we consider not only the cycles, but also the one-dimensional sheaves supported on them. And this relative geometry, in particular, the geometry of this vibration will tell you, somehow will tell you that the information of the genus. And this is the idea. So let me get, I will be more precise in the following. So then after you have this Hilbert-Chow morphism, then so there will be something so-called perverse filtration associated with certain cohomology of this modular space. And then this perverse, so then you have a vector space with a perverse filtration, and which I will introduce what it is in a minute. And this will give you all the curve counting invariants. And this is the current mathematical understanding of the Gopakumar-Vafa theory. All right, so before I go further, then maybe I start with an example, and this example somehow gives you the idea how to count curves using this vibration H. All right, so the example, this is like first example, which if we consider, this is like ideal situation where we are considering elliptic vibration with integral fibers, and we just assume in the perfect situation where even there is a section, fibers are integrals, and then this is X, which is fibered over a surface, smooth surface S, and we consider beta to be the fiber class. So this is beta is the fiber class. So this is beta. Okay. Now we want to calculate the curve counting invariance, and this is not a very difficult task if you do the curve counting invariance in this case directly using Gromov-Witten dt. It's been solved for a long time. So what's the expectation? So then after you have Gromov-Witten dt, you can get this. You can know you know what is expectation of this ng beta. So the expectation is, so for example, this is the genus 0, right? If you want to count genus 0 curve in the fiber class, then most of fibers are elliptic curve, and the contribution. So essentially, this the rational curves are contributed by the Euler characteristic. You can imagine up to a sign, these rational curves are contributed by the topological Euler characteristic of the total space, right? So this is the ng beta, which is negative of chi x, essentially the Euler characteristic, and 1 beta. Well, this counts how many ellipticals you have, and since it's parameterized by the base, so you can. It's not hard to imagine that this number should be the topological Euler characteristic of the base. So you get, this is the negative chi x, and 1 beta is as chi s, and when the genus is higher, then you should get 0, because for the fibers you cannot contain curves of genus greater than 2 in the fiber class. All right, so this is the expectation, and which is matched with the Gromov-Witten counts. So now let's see how to use the fibration here to get these numbers. Okay, so but in this case is nice simply because the geometry of this fibration is very easy. So since we are in this ideal situation, it's like, so you can imagine that for model of, so the one-dimensional sheaves on the elliptic curve, right? This is it's for fixed degree, it's parameterized by the elliptic curve itself, and then you have the relative situation. So this m beta 1, which this is parameterized model of one-dimensional semi-stable sheaves on these fibers. And this is actually can be identified with X itself in this ideal situation. And then the Hilbert morphism is simply remembering what's this point, right? You can have your cycles moving, and basically it's the same as remembering this point in the base. So this is just S. Okay, so in this case, this fibration is simply in the ideal situation where it's elliptic it's an ideal elliptic fibration with beta a fiber class, then this elliptic fibration, so this H geometry is exactly the same as the original geometry. So okay, now let's count curves. So since we are going to study the topology of this morphism, we do the decomposition theorem with respect to this fibration, and let's calculate it. So you push forward the trivial local system. So everything's smooth and smooth. The fiber, of course, is not. It has singular fibers. But okay, we push forward the trivial local system. So then by the decomposition theorem of Bernstein, Billings, and Junliang, well, this is an even simple case. We first have the trivial local system, which calculates. So this calculates the relative H0, right? And then you have a trivial local system. By the hard leftist, you should have also you have some a copy QS here shifted by -2. So you have QS here and QS shifted by -2, which are, so this is related by the relative hard leftist. Yeah. And then all the remaining things are just in this relative in some sense this summand. All the remaining summands are included here. So you have, this is a decomposition theorem. Well, then we organize this in a symmetric way, right? We just put as a formal parameter t, and we organize it. So you calculate the Euler characteristic of this one. You put t to the power of -1, and you put the Euler characteristic this one and this one. You make it a generating series, and since you have the symmetry simply given by the relative hard Lafshitz, you know there's also a symmetry for this Laurent series, or even it's like a polynomial. Then it's a finite terms. So then you just organize in this way, in the line I'm writing here. You make it as a like polynomial in the variable t to the power of -1/2 plus t to the power of 1/2. You expand it, and then you start to read the coefficients. The first constant coefficient is negative chi x, which is the genus 0 information. The first coefficient is the genus 1 information. They keep going, and the genus 2, then the other section is 0. So so just let me say one thing is that here you might be wondering, this V is pretty mysterious, right? So I haven't told you what is V, but you don't need to worry about it, because if we want to calculate any cohomological information of V, we can just use this equation, right? Because after we take the global cohomology, for example, then the cohomology, any cohomology of V can be, I mean, the K theory can be expressed as the cohomology of X and the cohomology of S. So you don't need to worry about it. You can calculate everything. And that's, if you do this, you will get this equation where you can, where the coefficients recover all these Gromov-Witten invariants for this relative geometry. Okay, so this is the idea of looking at the model of one-dimensional sheaf, then Hilbert-Chow morphism, then looking at the Hilbert-Chow morphism, the topology of the Hilbert-Chow morphism, and then this will give you, will count you the curves. Okay, so this is the ideal situation, as I said, because they are so nice that the target and the domain, they are both smooth. But in general, it's not the case. This M beta X chi, so the modular space, just imagine that you are considering the modular space of semi-stable sheaves on a threefold. So certainly it will be very, very singular. It won't be reduced and won't be irreducible. Oh, sorry, it won't, yes, it won't be reduced and won't be irreducible. However, virtually it's still, it's smooth, namely, so instead of considering the singular cohomology, there is some perverse sheaf called the BPS sheaf. It behaves like the trivial local system or the constant sheaf in the smooth case. So there will be a perverse sheaf which is self-dual. So this was introduced in the quiver setting by Davidson-Meinhardt and generally in this setting by Nobu-Toda. And then now what we have to do is to replace, so this somehow encodes the singularities for this modular space. And then what you do is you replace the original singular cohomology consideration by the BPS cohomology, which is the cohomology taking value in this BPS sheaf. And this is similar to as before, that this cohomology will carry a perverse filtration, which is simply given by the topology of the Hilbert-Chow morphism. And then this will recover all the curve counting invariants and G beta. So exactly this is the same story as I just showed in the previous page. The only difference is that instead of considering the Q, there will be a BPS sheaf which will do the same job. Okay, so more precisely here, I'm listing the formula. So this is the Hilbert-Chow morphism. Yeah, so this all the curve counting invariants can be determined by you do the decomposition theorem for not only for you consider the direct push forward not only for the cube but for this BPS sheaf and take the perverse cohomology, essentially use perverse truncation to cut it, and you make a generating series which will recover you all this NG beta.
Junliang, can I ask you a question? So the notation seems to suggest both for the phi BPS and the invariance NG beta that they do not depend on the other characteristic psi.
Yeah, this is a perfect question. Actually, this is the third part of the talk. I will explain. Spend more than 10 minutes to explain it. Thanks. Yeah, it's a good question.
Okay.
And the answer is the quick answer is yes. You are right. It won't be dependent on the extra things you choose.
You choose. Great. Right. Thanks.
Great. So okay. So this is the brief overview of well, it's not brief. It takes me 20 minutes or so to over the general story of the Gopakumar-Vafa theory. So in my point of view, the interesting perspective of this proposal is not only that it counts to invariants, it produces invariants, but also to make connections. It's like a bridge, because well, for a lot of geometries, the Gromov-Witten and Donaldson-Thomas invariants are already calculated by the direct ways. So in some sense, you know what this G and G beta, but so this Gopakumar-Vafa proposal in some sense is like connecting two complete different geometries. So if you do like Gromov-Witten, it's in some sense it's amazing that this will it will be giving you the same information as you do this way here. So I'm basically the second part. I'm going to list 3 cases. So in these 3 cases, in some sense, the Gromov-Witten theories are familiar, but the match between the Gromov-Witten theory and the Gopakumar-Vafa theory is really it involves a lot of interesting geometries I would like to explain. Okay, the first case is the local curve. So imagine we're in more than 20 years ago, and if we want to do curve counting invariants, probably the first case we want to try is local curves. You pretend as if your curve is embedded Calabi-Yau threefold, and so then how to get the information, how to get the curve counting invariants for the local curves. And in the Gopakumar-Vafa proposal, this is related to the Hitching fibrations, non-abelian Hodge theorem, and the P equals W conjecture. So I will explain this. So the second case is I will explain as the Gopakumar-Vafa proposal in the case of K3 surfaces. And this is relevant to the Lagrangian fibrations of holomorphic symplectic varieties or hyperkähler varieties. So I would suggest that maybe I should put this in the title of the talk. So okay, so the third part is the local P2. So local P2, as you can imagine, this involves the geometry of the model of semi-stable sheaves on a P2, and actually this also it will involve a lot of interesting geometry. In particular, this is relevant to the chi independence conjecture by P-Equals and also by Untitled from different perspectives. And also, amazingly, this is related to Engel's support theorem in his proof of the fundamental lemma of the long-length program. Okay, so let me start with the local curve story. So to start with, we consider C to be a Riemann surface of genus at least 2. We fix a Riemann surface. Then so the local Calabi-Yau threefold in that setting is the T star C cross A1, right? So you just make a curve. This is the easiest way how you make a curve into a Calabi-Yau threefold. You consider the total cotangent about the total space of the cotangent bundle across a trivial factor. And there is an easy choice of beta, which is that you just consider n times the zero section. Right? So you consider this Calabi-Yau threefold and the zero section. And then you make a choice, chi, such that, so for the first part, for convenience, I will assume n chi is co-prime, namely the chi is co-prime to this curve parameter. So later, in the last part, if we have time, I will explain how to remove that. Okay, so now after we made this choice, we can consider the model of one-dimensional, because of this choice, actually, we can do model of one-dimensional. So essentially we want to do semi-stable, but this choice forces us to have the coincides of the semi-stability and the stability. So we just need to take care of one-dimensional stable sheaves on this guy, given whose support is n times the curve and Euler characteristic given by this guy, right? So this is the modular space we will use to produce this curve counting invariance. Since everything is stable, so we know that this stable sheaf supported on this threefold, actually they are schemes theoretically supported on so the surface is actually surface across the points. So then this tells us that this modular space will also have a product structure. So you can simply ignore this A1 factor. So they are the model of one-dimensional stable sheaves on the T star C. With the support given by n times the zero section, Euler characteristic chi. And even, okay, so now, so this is a stable sheaf on the T star C. Actually, you can just push forward to the zero section, right? So then this gives you actually a vector bundle of rank n. And but the structure of the total cotangent, the cotangent direction tells you that this vector bundle carries an extra structure, which is the Higgs field. So this is actually the modular of Higgs bundles. So in summary, when we consider this local curve situation, then the modular space involved in the Gopakumar-Vafa proposal, the modular space involved is actually the model of Higgs modulus, the modular space of Higgs bundles. And okay, so now let's so this modular space in general is called the Dobot modular space from the theme of the Abelian-Hodge theorem. And it's not hard to imagine the Hilbert-Chow morphism is exactly the Hitching vibration. So now we see that there's a connection between curve counting for local curves with the topology of Hitching vibration. So here, essentially, the Hilbert-Chow morphism is the Hitching vibration where we simply attach E theta, the Higgs pair, to the coefficients of the characteristic polynomial of this characteristic of this Higgs field. Okay, so this is a space. This is a modular space which has been studied also intensively for maybe from different perspective, and they are smooth due to the choice that n chi co-prime. So this choice makes sure that this modular space is smooth, and in that setting we don't need to worry about the singularity, and that the BPS sheaf is simply the trivial local system up to a shift. Okay, therefore what Gopakumar-Vafa says in this setting, it says the curve counting invariants for the local curves, actually they are determined by the topology of Hitching vibrations. In particular, if you do the decomposition theorem there, it will calculate the Gromov-Witten invariance. Okay, so all right, so so the story here actually is summarized in this triangle. So the Gromov-Witten, so the left box, so this box is the Gromov-Witten invariance for the local curve T star across A1. So this is a subject which has been studied for more than 15 years, I think. So for example, this was the Gromov-Witten invariants were first calculated by Junliang and Rahul Pandharipanda. First, I think their degeneration and localization, and in particular, they show that they satisfy a TQFT formalism. I mean, this is the date, which is more than 15 years ago, I think. So, okay, so this is the left part. We can decide what these numbers are. However, the Gopakumar-Vafa theory, as I said, it's like a bridge. It tells you that these numbers are related to another geometry, which is the so-called the topology of the Hitching vibration. So they are the perverse numbers for the Hitching vibration. More precisely, you do the decomposition theorem for the Hitching vibration, and so every perverse the cohomology. So the Euler characteristic of every perverse cohomology actually. The Euler characteristic of every perverse cohomology actually are related to these numbers which were decided 15 years ago. And so this side is essentially it's calculated, and this side is completely mysterious. So because people have studied topology of Hitching vibration, decomposition theorem for Hitching vibration for a long time, and it's really not just something. In general, it's very hard to do the calculation simply because the fibers, the singular fibers of the Hitching vibration could be very, very complicated, and for them relevant to the Langlands program and so on. So okay, so now something known and something mysterious. You want to connect. Then the Gopakumar-Vafa theory says they are the same, essentially, or numerically. So and then there's in order to connect these worlds, there's a third party which was introduced and discovered. Actually, this was first realized, I think, by Tron, Diaconescu, and Pan. So there is a third party which is the Hodge theory of so-called character varieties MB, and which connects both worlds. So since so first of all, this Hodge I will give you more details, but this page is basically a summary. So the Hodge theory of character varieties. The character varieties are certain affine varieties where it has a non-trivial mixed Hodge structure. Then you can calculate the weight filtration. And these numbers actually, the weight polynomials actually are calculated. The dimension, so the weight polynomials of these calculated by Hausel, Rodriguez-Villegas, so via arithmetic methods, because of the description of the character variety via matrices, they use counting points over finite fields to deduce these numbers. And in short, there is some closed formula here which are which are matched with the Gromov-Witten formula. And by so this is realized by Tron, Diaconescu, Pan. And then okay, you can identify these two worlds numerically. But if you want to complete the Gopakumar-Vafa theory, then you have to connect this MB, the Beatty modular space, or the character varieties with M double, the Higgs modular spaces. And this is something which is not so mysterious, because certainly these two modular spaces are connected via the theme of non-abelian Hodge theorem. This is like a further refinement of this non-abelian Hodge theorem called the P equals W conjecture. Namely, it says that the topology of Hitching vibration actually are connected closely with the Hodge theory of the character variety, which I will introduce in the next page. So, okay, any question at this point? So simply I'm going to introduce the triangle which connects these two worlds. Okay, let's move to the next page. So this is the P equals W conjecture. So as I said, so this conjecture was certainly raised from a completely different motivation and perspective. The original motivation for having this conjecture has nothing to do with enumerative geometry, but this was found later that they are actually connected. So, and in particular, I think that at the very early stage of this conjecture, there was not so much evidence, and Tron, Diaconescu, Pan, their discovery was a very strong supporting evidence that the conjecture has to be true. So, okay, so now this is a completely different story. We fix the Riemann surface, integer n, which is the rank, Euler characteristic with this co-prime assumption. Then M double is the modular of stable Higgs bundles, which was the thing we introduced before. And M beta is a character variety. It's parameterized as a twisted local systems in the Riemann surface. So, and then the abelian-Hodge theorem gives you a diffeomorphism between these two modular spaces, which identify the singular cohomology.
Can I ask, how does MB depend on the curve?
It doesn't depend. Yeah, this is a good question. It doesn't depend, and this also makes life much easier. Yeah. So in particular, it allows you the arithmetic method to calculate these numbers. For example, So for example, in the simplest case, you can think of this as, for example, this is the total. A simple case is that this is the total cotangent bundle of elliptic curve, and this is just the C star cross C star. This is the rank 1 case, for example. And here it depends on the complex structure of the elliptic curve, and here it has nothing to do with the complex structure. Yeah. Okay, yeah. So then the conjecture, the P equals W conjecture says, so there's a perverse filtration. Basically, you do the truncation to this direct push forward complex, and this PK, which, as I explained, this governs the curve counting invariance for from the Gopakumar-Vafa perspective, and this is actually the same as the weight filtration for this side. So this is the P equals W conjecture by Di Cattado, Hauso, Migliorini 11 years ago, I think. And then so in particular, if you look back to this triangle, then since the closure formula here, they are matched. So if we have the P equals W conjecture, then this completes the Gopakumar-Vafa theory in this specific situation. Namely, you can you can move things from here, which are very mysterious, to here, which are a little more clear, and then you finally move here, and it's a match. Okay. So so the question here is reduced to another question called P equals W conjecture, which is still sometimes difficult problem, and it's still open in most of cases. And in this page, I'm listing some progress towards this question. So this is the conclusion: the P equals W for GLN, this group, rank n, and the Riemann surface C. This will imply the Gopakumar-Vafa Gromov-Witten match for this local curve with this beta n times 0 section. So in particular, this reduced this question to this question. And this is some cases which are known. So GL2, arbitrary genus, this was the original work of Di Cattado, Hauso, Migliorini. And when higher genus, when genus n, and for the genus 2, this was the work, my joint work with Mark Di Cattado and Devesh Maulik 2 years ago. And then for general arbitrary G and arbitrary n, we have some we know part of that. So for the entire cohomology, we know part of it, which satisfy the P equals W, but still there are mysterious parts that which are not completely understood. So this is since this is not a P equals W talk, so I will keep it brief and move to the next story. Okay, the next story is the K3 surface. So the idea here is that simply, so you can think of this as the previous case is the local curve, right? Total cotangent bundle of the Riemann surface. So sometimes this can be viewed as a local K3 surface. And when you study a local K3 surface, there's natural questions whether you can move to a real K3 surface, like a projective K3 surface. So this is what I'm doing here. So, and we will see that this actually is relevant to another, this is relevant to another story. So XS is a K3 surface, namely smooth projective. Well, this is actually I think the password for this seminar. So I suppose everyone's very familiar with it. So the smooth projective surface with trivial, simply connected with trivial canonical bundle. And then we can, this is identical to what we did before. We just make a local Calabi-Yau for the S cross A1, and we fix a curve class on the K3 surface. But now this is not just fixed by an integer n, like in the local case, but you just choose any curve class in the K3 surface. Then as before, we choose the Euler characteristic chi, such that chi is co-prime to the divisibility of beta. So the purpose here again is that at this stage, I don't want to involve strict semi-stable sheaves. I just want to keep everything stable. So we do the same thing as before. So M. So the only thing the only thing I'm changing here is that I replace the T star C by K3, and everything works identically. So this one-dimensional stable sheaves on S cross A1 with support beta, polar characteristic chi. And so it admits a product structure, the one-dimensional stable sheaves on the K3 with fixed support and polar characteristic cross A1. Okay, so this is a parallel story. And in this case, the Hilbert-Chow morphism is given by so-called the Bowie-Mukai system. So again, this kind of model of one-dimensional sheaves on K3 surfaces admits a natural morphism which sends a sheaf to its the supporting cycle, right? The fitting support, which lies in the local system. Which lies in the linear system of this S. And this is a projective space. And in particular, this is a Lagrangian fibration with the total space a holomorphic symplectic manifold. And again, due to the assumption, the coprime assumption, this is a smooth holomorphic symplectic manifold. And the BPS sheaf is the trivial one. So you don't need to worry about this thing here. So therefore, the Gopakumar-Vafa proposal tells us that the BPS numbers, the curve counting numbers for K3 surfaces are governed by the topology of this Lagrangian fibration. So in particular, so there's a connection here. So again, the entire story is summarized in this picture, which is a triangle. So let me start with the left-hand side, and surprisingly, it's always like the Gromov-Witten series are first attacked it. So here the left-hand side is the Gromov-Witten invariance for K3 surfaces. You want to, for any beta and G, you want to get these numbers. And this was in physics, this was the Gopakumar-Vafa conjecture in 1999, which is the formula expressed that all genus Gromov-Witten, the generating series of all genus Gromov-Witten invariants in terms of certain Jacobi forms. So roughly speaking, there is a closed formula which governs all the invariants. And this is actually, this formula was predicted a long time ago, and now it's proven by Panda and Thomas in 2013, which is very long paper. But this anyway, so this side is completely understood. It's a closed formula here. So now the Gopakumar-Vafa theory tells you that you have a bridge which is connected to another story which concerns the decomposition theorem for Lagrangian fibration of certain holomorphic symplectic manifold. And surprisingly, again, there is a third party which comes into the story which helps you to connect these two. This is actually direct check. So the Gromov-Witten invariants for K3 surfaces, the generated series of Gromov-Witten invariants for K3 surfaces, actually they are matched with the Hodge theory, in particular the chi-y genus of the Hilbert scheme of points, a Hilbert scheme of points on the K3 surface. So it's just a match of closed formulas, because here everything's calculated concretely by Goethe formula. So you have a concrete formula here, and it was realized long time ago that these are matched. And when I was a graduate student, I first saw these two actually. So I was reading the paper by Rahul and Richard, and so this was in the first page, like in the introduction, and actually, so I saw this connection, and I was very curious how to explain this phenomenon. And actually, somehow later, much later, then we realized that this is connected to the Gopakumar-Vafa proposal, namely. So we can always move things from here to here. And then in order to connect this with the Lagrangian fibration, we need also some statement parallel to the P equals W, namely, so the perverse filtration for such a Lagrangian fibration should be matched with this Hodge theoretic data for the Hilbert scheme endpoints on the K3 surface. Okay, so this is a triangle which, in my point of view, is parallel to the previous triangle. And so this is the relevant theorems. And because for compact hyperkähler manifolds, we have more tools. And that's the reason, so this triangle is completely solved, unlike the previous one. So this is the main theorem, which is in a joint work with Junliang. So, The upshot is that if we have a Lagrangian vibration for any compact hyperkähler manifold, then we can get these perverse numbers associated with this pi, which are essentially the cohomology of the perverse summand, right? You do the decomposition theorem, you pick every summand, and then you just calculate the cohomology. And these are the numbers which should govern the Gopakumar-Vafa invariance. And the theorem is that these numbers exactly are the same as Hodge numbers of the total space. There's nothing to do with the Lagrangian vibration. So here, the left-hand side relates, it's connected to the Lagrangian vibration. The right-hand side is only a Hodge theoretic. And in particular, here, the reason I call it P equals F is the F denotes stands for the Hodge filtration. Okay. And the conclusion is that so after this theorem is proven, then we complete the Gopakumar-Vafa and the Gromov-Witten match for K3 surfaces so these are the numbers which governs the Gopakumar-Vafa invariance or curve counting invariance. And by this theorem, it can be expressed in terms of the chi genus of the total space. We can forget about Lagrangian vibration, only consider the chi genus of the total space. Since those holomorphic symplectic manifolds are deformation equivalent to the Hilbert scheme of points on K3, then we can further move to the chi genus of the Hilbert scheme of points on K3. And then we get this closed formula, which was explained in the previous triangle. So we can move something here, this is something hard, which is to calculate the decomposition theorem to something which was calculated a long time ago. Okay. In particular, we know that Gopakumar-Vafa and Gromov-Witten match for K3 surfaces is true fully. But actually, I was a little cheating here as the question raised by Julia. So here I always made an assumption which makes our life better, right? So we always, at the beginning, I always made the assumption that the Euler characteristic is co-prime to the curve classing in some way. And this tells us, and this assumption will simplify our lives a lot, because then we won't see any strict semi-stable and singularities in the modular spaces. And the third part of the talk, I will explain that this singularity is actually a very important rule, and this is relevant to some interesting geometries. Okay, so this is the third part I will discuss, and I will focus on the geometry of local P2. Okay, and
but Junliang, can I ask? I mean, in that previous page, you're happy with beta being non-primitive, right? That doesn't, as long as you pick this chi properly.
Yeah, so beta could be anything, yes.
Yeah, as long as this chi is picked properly, so you have stability.
Yeah, that's right. Yeah, there's no assumption on the class beta at all. Yes. Yeah, thanks. All right, so local P2 now. So the first place I started to be interested in this question actually is from the paper by Maulik-Toda and from also from the paper by P Equals W. And also I appreciate them for a lot of interesting conversation on this topic. So and okay, so for the Gopakumar-Vafa proposal, we had a choice, namely the choice of the chi, which seems to be a strange thing, that we made a choice at the very beginning, and the number should be, I mean, more strictly, it should be called ng beta chi, right? Because you made the choice of chi, but before I simply omit this notation. Now I want to put it back. General question: which chi should we really start with? Is there a canonical choice of the Euler characteristic which will make the entire story work, or which will produce as the correct numbers? And so, I mean, this is a very long story. I think even this dated back to Sheldon Katz's proposal in the genus 0 case, and even later, I think, for example, Maulik-Toda's proposal for full generality for safety, they suggest that, okay, we start with the chi is equal to 1. So this is some choice of chi which can always ensure that the stability is equal to semi-stability. So this is a safe choice. However, there's an amazing conjecture by Yukinobu says it doesn't matter which chi we start with. Namely, simply the Yukinobu's conjecture says we can start with arbitrary chi, and we will get the same number. So if you're familiar with the holomorphic symplectic geometry, you find this is very strange, because if you, so if you consider a K3 surface with a class 2 beta, beta with a primitive class, and if you choose the Euler characteristic to be 0 or Euler characteristic to be 1, and this is a familiar geometry, and this is a singular holomorphic implied variety whose calculation actually in full details can be found in the paper by Julia and so Mark Decatado, Rob Saka's paper in the calculation of O-grade 10. So they actually calculate the cohomology of this one and the intersection cohomology and found that actually they are different. However, so here this is the amazing part is that this is the BPS sheaf here should somehow correct you this difference. So which means no matter which chi you choose, and if you involve this BPS sheaf, then this will give you the correction term, which tells you that the cohomologically there's no difference between the different modular space of semi-stable sheaves. So for different choices of the.
But how do you state this conjecture? I mean, it's saying that he conjectures that there is an appropriate choice of this BPS sheaf that will make this conjecture true.
No, sorry, I didn't say that, but the BPS sheaf was constructed uniformly, modular some conjectures on the orientation data. So for any, okay, so I can say this. I can say this briefly. So the rough idea is that when you have you have a stack which maps to the coarse modular space for this is for arbitrary chi. Then the stack is roughly described as the critical locus, where you have a vanishing cycle sheaf upstairs. And my understanding is that you just push forward this to the coarse modular space and choose a certain perverse summand. And this will be the BPS sheaf, which is constructed uniformly. And then the conjecture is with this given BPS sheaf, then this cohomology is independent of the choice of chi. Rahul, is that okay?
Yeah, sorry, yes, I was muted.
All right, okay. Yeah, thanks.
Sorry, and in particular, you don't ask chi to be co-prime with.
No, that's the entire point. The chi could be anything. Yeah. This is really, even now, this is rather mysterious to me, and I'm still trying to understand this well. But okay, to understand, let's start with example to see what's going on here. Okay, now we consider so X to be the total space of the cotangent total canonical bound of P2. So this is a local P2, and the beta is D times a line. Okay, so here you have a local P2 and the D times a line. And so in this case, due to the final condition, namely since this KP2 is negative, and so here this is also it's not ideal, but it's also a good situation, namely the semi-stable one-dimensional. There would be strictly semi-stable one-dimensional sheaves on X on this threefold. However, it will be scheme theoretically supporting the zero section because of the negativity. So meaning that although there will be strictly semi-stable objects, but it will be a surface geometry. So it will not really involve the threefold geometry. Yeah. Okay, so now in this case, so M chi beta X this is the modular. Actually, this is also a very classical modular space, which was studied by people who are interested in strange duality and so on. So this is the modular of a semi-stable one-dimensional sheaves F on P2 who support this D times line or like with this chi. So this is a very classical modular space. And as Julia just mentioned, there are two completely different types of geometry involved. One is that when the D and chi are co-prime, so then in this case, stability condition coincides with the semi-stability, and you have a smooth modular space. In particular, when you have a nice choice of the degree, the curve class, or sorry, once you fix the degree, the curve class, if you have a nice choice of chi, then the modular space will be smooth. However, you have once you fix the D, you have more than half of a chance that you will get some non-smooth, the singular modular space. Because when the co-prime condition breaks down, then the stable locus will be strictly containing the semi-stable locus, where the strictly semi-stable locus will contribute the singularities of this modular space. So they will be singular. Okay.
So, can I ask another question? So do you have some kind of Ngo support theorem for this BPS sheaf?
Yes. So in this case, yes, and this still be on the slides. I think next or next one.
Oh, okay.
Thanks. Yeah. Okay. Okay, theorem. theorem, and this was this identity itself was conjectured by P. Equals, and he proved this also he proved this in certain cases using scattering diagrams, and we are actually proving it using what Julia just said, the support theorem. I'm going to expand this in a minute. So okay, so the theorem is that for any chi and chi prime, so okay, for fixed degree D, which is the curve class, and we consider the model of semi-stable sheaves with degree with the support given by degree D curve and all equals to chi. Then for any two choices of chi and chi prime, just choose two arbitrary numbers. Then the intersection cohomology. So let me just write this down. Intersection cohomology of these modular spaces are the same, and even the isomorphism is compatible with the extra natural information like the perverse and Hodge filtration. So basically, cohomologically, you cannot distinguish these two spaces for different choices, chi and chi prime. Okay, so here's the reason how here is how it is connected to the original the original Gopakumar-Vafa proposal. So when X is a total cotangent bundle of the total KP2, beta is this an arbitrary chi. Then Sven-Meinhardt shows that in this setting, the BPS sheaf is simply the IC sheaf. This is generally wrong. So this is not always the case generally. However, in this specific setting, namely, it is true that the BPS sheaf is the IC sheaf. And in particular, the BPS cohomology is exactly the intersection cohomology. And this is the reason we expect such a phenomenon as true. And this is supporting, the statement which supports the chi independence conjecture also by Toda. And I mean, the concrete form here is conjectured, I think, by Pirik. So any questions?
But are these claims also true for Fano surfaces, or?
Yeah, exactly. So yeah, these claims are true for final surfaces. And for Calabi-Yau, it's wrong. Like for K3 surface, you really need non-trivial correction terms given by the BPS. But for Fano, yes, it's true. So this is actually what's on the next slides. So actually, what we prove is like a support theorem, which I will explain in a minute. Probably, maybe you can ask me after. I don't have much time. So actually, this is a phenomenon for Fano surface, so which means the modular of semi-stable sheaves, and so we also have the chi independence for the intersections cohomology for model of semi-stable one-dimensional sheaves on any toric the petal surface is S. So for example, P1 cross P1, and you blow up P2 at 1, 2, 3 points. So also, but this is actually we hope that this we expect this is true for arbitrary Fano, but which means it should also recover the case where you blow up like 4 points, 5 points, and so on. But for some technical reason, this is so far what we can prove. And for example, this implies Toda's conjecture for the total cotangent amount of KS. And also there is a parallel story about the model of Higgs bundles. So Higgs bundles, so you can think of Higgs bundles as the model of one-dimensional sheaf on the total cotangent bundle, which is like a Calabi-Yau. So this is parallel to the K3 surface, and analogous to the K3 surface. It's like a Calabi-Yau situation. However, there is a way to make it like Fano. So this is to twist it. So we choose some effective divisor of degree greater than 2G minus 2. Then we consider Higgs bundles of this kind, E to the E tensor OCD. And these are, in my point of view, are close to the Fano, the model of one-dimensional sheaves on Fano surfaces. And we also have the statement here. Okay, last slides, I will say briefly about the proof. The proof is to use the Ngo support theorem. So the idea is that, for example, for the D and P2 and chi, we have the Hilbert-Chow morphism, right? So this is simply to the local system. And there is an open part this is the open subset which parameterizes smooth curves in the local in the linear systems, smooth degree D curves. And over this U, we understand everything very well for this model space. In particular, singularities do not come into play. So then we prove a type of support theorem, which shows that decompensation theorem of intersection cohomology, this will split into so intermediate extension of local system, which are, this is a support, this L alpha are local systems only on U. Okay, in particular with some shift. In particular, we know that this entire model, although so you see that although over this smooth locus U, there's no singularity at all, but everything essentially is determined by that. And this gives you the proof of the chi-independence. So here, the way for proving such a statement is to use Engels' idea to prove a type of support theorem. And Engels' original support theorem essentially works for smooth ambient space. What we are doing here is that we allow this modular space to have singularities, but the singularities cannot be arbitrary bad. So we need some control of it. So the essential structure we're using is that the modular space, although itself could be singular, but this is the coarse, or even more precisely, the good modular space of smooth arting stack, which sits above it. So, and you can see, so in the case of model of sheaves on P2, then the smoothness of the stack level is given by the extension, the vanishing of extension 2. But you see this actually fails in the case 3. In particular, in the case 3 setting, so our support theorem does not work in the case 3 setting. And this is the reason that you cannot expect that the IC sheaf, the intersection cohomology have this chi-independence. And that is the case where, I mean, in the case 3 or the real Higgs bundles, and that is the case where really the BPS sheaf should come into play, where you will have a lot of small support sheaf on the boundary, which still, I mean, after you collect everything, it still will give you the chi-independence phenomenon. So I'm sorry, I was a little rushed in the last part, but I hope so. Thanks for your attention. I'm stopping here.
Thank you very much for this great talk. So, yeah, thank you. So, any questions? Any questions about the talk?
Yeah, can I ask? Can you go back to the previous slide?
This one?
So one is a small question. So the smoothness of the art stack there is because it's Fano, right? That's why you get the vanishing.
No, that's extension. That's extension of 2. So in the Calabi-Yau, this is to home. This is due to home.
Yeah.
And yeah, this can jump because of the the polystable sheaf.
Sure.
So, yeah.
And so then the statement on the full support, how do you prove that? Because I imagine that the fibers are not necessarily irreducible. Because then, can you say maybe a couple words how you get that the push forward of the IC sheaf is just...
Yeah, so the proof is very, essentially it's very similar to the proof of Engels' support theorem. Well, more precisely, there is support theorem by Lemon and Chaudois.
Mm-hmm.
So for, I mean, in their case, it's about smooth setting, but still so okay. So let me say briefly the idea. Okay. Yeah. So one of the, I think this is the typical situation we can. So I'm talking about a smooth case, but actually, so we consider, yeah. So this is the case we consider a versal deformation of a banana curve. So we can smooth it at one locus. We can smooth it this way, and the other we can smooth it the other node. Okay, something like that. And the generic fiber is an elliptic curve. So here the central fiber could be very complicated, and so but the base is dimension 2, fiber is dimension 1. In this case, actually, this point will not be although you have this non-integral fibers, this will not serve as a support. Mm-hmm. Simply the reason, this is like a duality, that's art of duality. You play with the duality, you see that if you have a support there, there's no correct shift will make this happen. Okay. And then this is a similar story for, so you see here only but
that's true for the base of the versal deformation. If you cut a slice through that point, you get
exactly. So this is like the Fano condition. And if you cut the slides, you get the one basis dimension 1, fibers dimension 1. So then you will have a new support. Mm-hmm. Right. And this is like the case 3.
I see.
Okay. Yeah. So yeah, thanks for the question.
Thank you.
Hey, can I ask something, Junliang?
Yeah, sure.
So in Pieric's work, that conjecture and that geometry came up in part of the proof of this Takahashi for P2 relative to E.
Yeah.
So if you know now for these other Fano examples, maybe this is maybe a question more for Pirik. What does it, I mean, how much of the obstructions for doing the proof for these other Fano surfaces?
Yeah, is Pirik here?
Yes, I can.
Okay, yeah, go ahead.
Say something. I mean, so for the Takahashi question, I only needed the the Kie-independent conjecture, which was talked about today, but which was already known somehow from local P2, just as a numerical level for the numbers. Yeah. And Chi beta, it was already known. And so I used that to prove Takahashi in local P2. But now what they proved, what Junliang and Davesh proved, is a cohomological statement. And for example, this thing implies the higher genus version of Takahashi conjecture with lambda G insertions.
But what about for P1 cross P1? I thought even for...
Yeah, so for P1 cross P1, so the Kie-independence was also known.
Oh, I see, I did.
And so why it's not done, it's only because like the scattering diagram story is not completed. But some of the Kie-independent story was...
yeah, this is more, my understanding is more relevant to the higher genus. This part is more or less...
Yeah, that's why what is new now is that for local P2, the higher genus version of Takahashi conjecture is known by the work of Davesh and Junliang, which was not known before.
Thanks.
Okay, cool. Any more questions to the speaker?
Maybe I have a question. So you said that the fact that the BPS sheaf is the IC sheaf holds in the Fano case, but in the K3 case, you have some correction terms. Could you just say maybe a couple words about that?
Yeah. So this. Let me turn to the page I was writing. So the rough idea is that so you have the this is a stack and this is the coarse modular, or even more precise, the good modular space. And so locally you can write this modular space is the critical locus. Sorry, the stack is a critical locus where we have this vanishing cycle sheaf. And so the first task you need is that you want to glue this sheaves, which will require some orientation data. And in the work of Maulik-Toda, essentially, that tells us that which kind of orientation data one should use. And but in general, this is still open. Why there exists such kind of orientation data? But for local surface, I think it's okay by work of. Then you can get a global like vanishing cycle sheaf, and I think what you do is you push forward phi f and the perverse 1, and I think essentially this is like maybe up to some shift. This is the BPS sheaf. So you consider the difference between the stack and the scheme, and you do the push forward and choose a specific perverse. You choose a specific perverse summon. So you can imagine what's happening, right? So if you have a smooth, if everything's stable, then this is like a GM jerp. So I mean, this is like a trivial GM jerp. So you don't. So essentially, you can do everything directly on the scheme side. It's no big difference. But now, when the fibers of H could be complicated over this strictly semi-stable locus, where the fibers are complicated, and in particular, this BPS sheaf will be different with the IC sheaf. So if you restrict over if you restrict yourself over this so stable, where this is a GM jerp. So in that part is simply it's just simply IC or Q. But then you see that when that the fibers are more complicated, you will have more correction terms, and this is how. And more precisely, this correction terms will be supported on the singularity, right? So the point where the fibers are more complicated. And yeah.
Thank you.
You're welcome.
Maybe I'll ask another question too then.
Sure.
For this Toda conjecture for the Chi independence.
Yes.
In what generality can that be stated now? If you have to let's leave orientation aside, because that's going to be a persistent issue. But in what generality can you state that modulo orientation?
But I think this is the only issue in some sense, right? So yeah, so
you can state it for any
any Calabi-Yau threefold, I think. Wait, so let me turn to that page. Yes. So, well, more precisely, Toda's conjecture does not say directly for this cohomology. This entire, I mean, this is certainly stronger, but he just says no matter which chi you start with. So okay, so you can put a chi here. So then you will put a chi here.
Oh, I see.
And then these numbers will be, so yeah, these numbers actually does not depend on a chi. So.
But so then maybe the correct statement is there exists a choice of orientation which will make this true somehow.
Yeah, but this is completely about the choice of orientation data. But so Devesh and Yukinobu, they told us how to make such a choice, right? So that's Calabi-Yau.
Yeah, maybe you're right. That's right.
Can I also ask a question?
Sure.
You constructed this isomorphism, and is that isomorphism canonical in some way, or is that?
If you try very hard, you can make it canonical because, yeah. So what is the where this isomorphism comes from? As this is where I was answering. So where I was talking about the decomposition theorem. So the isomorphism comes from that you over this U you have this this is a relative Picard variety, right? So this is the relative Picard variety for the curve. This is how do you call it? F. So then this isomorphism comes from that everything's given by the IC extension of the push forward of Q of this Picard. And so the chi independence is given by the fact that for Picard variety, the local system given by the local system that calculates the cohomology of the Picard variety does not depend on the choice of chi. So the easiest way to see it, actually, this only depends on the curve. So this is, you have the curve, and this is G. So it's R1, G star Q, C, and you do the wedge. So every cohomology of the Picard is given by this way. So if you make a choice, I think essentially you can make this more or less identical. More or less canonical to identify the cohomology of the curve with the cohomology of the Picard. And then every other, you don't require any other choices, I think.
Thanks. I have one more culture question. So regarding the Gromov-Witten and Donaldson-Thomas at the beginning. So there was a story of Pandey-Thomas stable pairs, which was supposed to be a bridge between the two theories. So where does it sit anywhere in this new developments?
This is actually it's a very good point actually, because yeah, this is yeah. Let me go back to the first page. Thanks for the question. So so this is what I'm talking about today is really some shadows of this theory, and so the final purpose is really want to establish a connection between two different kinds of geometry. One's here, the other is here. So or more precisely, for every Calabi-Yau threefold, you want to prove such an identity, and this is the final. This is the goal. And but if you want to do Gromov-Witten theory, it's really hard to make a comparison to this geometry, right? But in some sense, the PT theory is the better way to really make a connection, because if you just consider a single curve, then the Gopakumar-Vafa side is, you can think of this as like a competitive Jacobian. If you just consider a versal family of curves, for example, then the Gopakumar-Vafa theory, I mean, this is a local story. The Gopakumar-Vafa theory is really like the family of competitive Jacobian. And the PT theory is really like the relative Hilbert scheme associated with this curve. And there was a lot of work along this direction, which says that these two worlds are closely connected. This, for example, date back to the work of Thomas and Shen, Migolini, Maulik-Toda, and a lot of other people, which actually somehow explains that why the relative Hilbert scheme geometry was closely connected to the relative competitive Jacobian geometry. And this is, I think, a local model for the Gopakumar-Vafa PT correspondence, in my point of view. So.
Yeah, thank you.
Yeah,
So I guess if there are no further questions, yeah, thanks again for the great talk. We can hang out a little bit in the Gather Town if people have time and have some more discussion there. So I just put the link in the chat.
Okay, I'll be there.
Yeah. Okay. Thanks. Thanks again.
Thanks.
Thanks everyone for coming.
Yeah. Should I just leave this?